starting off the new year with something that's kind of easy. Quite frankly, this is review of a grade 9 idea, and nothing that we do with it is all that more complex than what happens with it in grade 9. You'll understand as we get further into the unit why that is, like why we talk about average rates of change. So, but really today is just a little reminder about how this works, and a nice easy day for the first day of January to get started and get warmed up a little bit again. So one thing that's kind of interesting to think about, there is sort of some deeper understanding that's going to come around this topic, but like after we look at other stuff starting tomorrow. Okay, so for now, as I said, it's really just grade 9, but there is sort of something, I think, some deeper understanding that's coming when we compare this grade 9 version to the grade 12 version that we're going to start later. So you could come back after a few days, like later this week, you could come back and think about this little scenario that we're going to talk about here, and sort of get some perspective on how these two things that we're going to be working on in this unit, really there's two main things on how they are different from each other, how they're the same, that sort of thing. So here's our scenario. We have two people who are driving in their cars, and Alec travels 240 kilometers in 3 hours at a consistent speed. So what does that work out to? This is really important always. We've talked about that a little bit in this course, but this little formula that relates distance, rate, and time. So rate is equal to distance over time, and that's like kilometers per hour. It's amazing. You probably know this. You're probably very good at this now that you've taken lots of science courses, assuming that most of you have. But units are really, really important, and they can actually tell us a lot about simple relationships. And that's the units is something that you could also use, I would say, in this course for what we're doing in this unit on rates of change. Okay, so here we go. The distance was 240. The time was 3 hours. So the rate works out to 240 divided by 3. So that's 80 kilometers per hour, right? That's how we do that rate. Pretty straightforward, pretty simple. So this is Alec. So I'm picturing this person took like Highway 7 or something like that. So they didn't take the 401. They traveled 80 kilometers an hour. That's a slower speed, but it was consistent, no traffic, that sort of thing. Okay, consider the next person. Gurpreet started out on the 401, let's say, so driving at 120 kilometers in 1 hour. So 120 kilometers for 1 hour, and that is 120 kilometers per hour, right? Then hit traffic and only traveled 60 kilometers in 90 minutes. So then traveled 60 kilometers, 90 minutes, we're gonna think of that in hours, so that's 1.5 hours. And 60 divided by 1.5, what's that work out to? 40, very good. So that's 40 kilometers per hour. Okay, then traveled 120 kilometers per hour for another half hour. So that would be 120, right, for half an hour, 0.5. So I want to think about something that happened here. Just put your pencil down and watch. Don't write this down yet. If I take the average of Gurpreet's speeds, what do you get? So 120 plus 120 plus 40 divided by 3. Can somebody quickly do that? I should have my calculator out. What'd you get? 93.3333, like that, yeah? Okay, so the 93.3, like I said, don't write this down. Do you believe that's the average speed that this person traveled on this trip? Do you believe that? What do you think?
No, they travel at the different speeds, different amounts of time.
Different amounts of time. So if you were thinking of this as a weighted average, there is actually more you could do with it here. Like you could think of it as a weighted average and actually, you're right, kind of get.
Although actually they did do the same amount of time in the gap though, 100 hours.
What are you saying here?
That if you add the two that are 120 kilometers per hour, they actually travel the same.
Okay. So although one of them we added twice,
That's true.
and so like there is something fishy going on here. But really the point is, when you have a rate, this is not how you find the average. Okay? You don't find an average rate by adding up rates and dividing. What is average speed here? Average rate of change. It's over the course of the entire trip. How far did they go and how long did it take? So here is Gurpreet's trip. Traveled at a fast speed. I can see the slope. Remember, rate of change is like slope, right, from grade 9. It's the same kind of idea. So the slope, traveling at a constant speed for the first hour, that was 120 kilometers per hour. Okay? And then traveling at a slower speed for an hour and a half, and then for half hour at a faster speed. Look at how far in total Gurpreet has traveled. So let me add this up. How much? First of all, we have to figure out what this is. We haven't figured out that yet. What is 120 kilometers per hour for half an hour? 60. So what's 120 plus 60 plus 60? Is that 240? And what's 1 plus 1.5 plus 0.5? It's 3. So what's the average speed? 240 kilometers an hour for 3 hours. That's wrong. It's 80. Just like Alec. So it turns out that these situations are designed in such a way that they're exactly the same. One person was traveling at different speeds along the way, but it turned out to be the same as the other person traveling at a sort of a slower but consistent speed. And let's take a look at that graphically. When I turn on Alex, look. So they got to the same location at the same time. Now, what is all of this nonsense? Like, what are we talking about? What am I getting at here? An average rate of change. In this case, the rate of change we're talking about is speed because of the units that we're talking about. But an average rate of change ignores what happens between the 2 points that you're looking at taking the average rate of change for, right? So if I look at just the beginning and just the end, the average rate of change ignores all the speeds in the middle. All it cares about in this case is the distance that was covered and how long. It doesn't matter at what rates that was happening along the way. Does that make sense? So average rate of change, we just take the end points and we just find we find the average. And essentially what we're doing, you'll notice, is using the slope formula from grade 9. Okay, that's all that today is for average rates of change. But there is something more profound sort of coming when we do the new stuff, where you can step back and think about, okay, now I understand how average rates of change is like this, and the new stuff that we're doing is like that. And I mean, they're sort of measuring the same thing, but then they're sort of not, right? And I think it's really important. I think sometimes we take things for granted that they're simple, and so we gloss over them, we don't really think about them, and then, questions that are sort of digging at understanding, we don't understand, they go over our heads, and we're not successful on them, that kind of thing, right? And there's like some kind of understanding that's lacking. So this is an interesting idea to, if I looked at this graph at any other time, right? Pick a random time, after an hour, or after 45 minutes, or after 87.5 minutes. I would look at that and I could see what their average speed was at that time using the graph. But if I'm just looking at their average speed over the course of the entire trip, I'm only looking at the end and I'm only looking at the beginning, right? The two ends of the interval that we're talking about. Okay, so let's take a look at this. Here's our first example. You do want to write this down. I'll give you a second to do that because there's some data there. Some of the questions for the practice today give you a table with data. This one gives us the formula as well, the function as well. But so if you're given the data, well, half the job is done and it's really easy to do the work. If you're not given the data and you're just given the function, then you have to find the values yourself. Okay, so it's giving us intervals. Find the average rate of change over each interval. So you might go ahead and think about which one's x, which one's y. Average rate of change or slope is rise over run, right? So you got to get the variables in the right position. And what I'm going to call that, you probably know this symbol, delta H over delta T, right? The change in H over the change in T, that's what the triangle means, delta. So at time 4, H is 380, so I start with 380 minus time 2, 320 over 4 minus 2. So the range, or the domain here that I'm being given, the interval here, is like my x's. That's my run, so that goes on the bottom. This is the change in height over time. Again, this is what I'm saying is, I think it's really important throughout the, as you're practicing this and throughout this entire unit, is always be thinking about what the rate of change is, what it represents. Like, think about what's actually changing, okay? And it's often over time, but it's not always, but it often is. But what's changing over time, and what does that mean? And especially if you're taking calculus, because this unit leads directly into the beginning of calculus, the stuff that we're doing right now, okay? So 380 minus 320, 60 over 2 is 30. Good? Okay, go ahead and do the rest. You remember from grade 9 that order is really important. You got to get you don't always just subtract the bigger one minus the smaller one, right? Order certainly counts. Does that look okay to everybody? 3 pretty easy questions. See, this is what I mean. That doesn't actually get that much harder than this. This is about what we're doing today. It's pretty easy, especially when you're given those numbers. But I would encourage you to think about it. So I'm going to graph it, and then we're going to talk about, yes, what these values actually mean. Yep. It kind of depends on the question for this. We're going to talk about what it means in a minute, so then we are going to talk about units. I would say usually it sort of depends on what the question is. If the question is given like this, it's important to think about units. So even if you're not putting them in your homework, you should be thinking about what the rate of change is, as I said. Okay, so let me plot these points. 0 and 220. I hope that this is, yeah, a good scale. Okay. Oh, I've got it here. Two and 320. You can probably just watch this too. You don't necessarily have to like draw a pretty graph for this. This is going to be just a thinking exercise. 4 and 380. 6 and 400. 8 and 380. 10 and 320. 12 and 220, and then 14 and 80. So what happened here? Well, we knew that, yep, sure. We knew this function was quadratic. I mean, you know that things falling follow quadratic paths, right? But we were given the function there, so we saw that it was quadratic. We could do some work if we needed to with that function. We have a lot of skills for that. But really, we just want to look at this. So what exactly does this mean? The first one was from 2 seconds to 4 seconds. So the first one was that. Right? That's the average rate of change. But between those 2 points, the path was actually curved. But if we're doing average rate of change, all we care about is the average. Let me see if I can draw this curve in. I think that'll be helpful to have. Whoop. Okay. The next one. So what does that mean? 30. What does that mean? $30 meters per second. Good. Yep. 30 meters per second. Okay, good. What else does that mean? Okay, good. Yeah. So 30 meters up. I like that. The average was 30 meters up each second. It was going for 2 seconds, so it was 60. I mean, that's the way the math worked out, right? It was a change of 60 over 2 seconds. But each second, it wasn't moving at that speed. Just the average for that interval. Okay, good. What is the next one? From 12 to 14, so from here to here. My graph missed, my sketch missed, but that's okay. It actually makes it easier to see both lines. So what happened there? So at an average rate of 70 meters per second, it was moving down, right? So again, there's nothing super profound here. It's not all that crazy. We do this in grade 9 where we talk about if it's a negative slope, it's going one direction. If it's a positive slope, it's going the other. In this case, interpreting it, negative means its average distance is going down. Positive means it's going up, that kind of thing, right? And what about that last one? So what was it again? Oh, I've got it right here. 4 to 8. So from 4 to 8. So the average distance that it traveled was 0. But it did move during that time. It's just that its average height, change in height, was 0. Because we happen to pick 2 times where it was at the same height. See, this is what I mean, is if I just tell you that the average change in height is 0, we don't know remember back to this idea, we don't know anything about the specifics between those 2 ends of that interval that we're talking about. We just know that it started and ended in the same place. It ended where it started. What if we picked 2 intervals like this? What if I picked like that? So the average would be negative, but during that time it went up for a little while and then came back down and just ended further down, right? So the average again is just thinking about the endpoints, not telling us anything about what's happening in the middle, and that might be fine. That might be what we need. That might be all we care about. Businesses look at all kinds of things. They look at their average, money that they make over the course of a year, over the course of a month, over the course of a quarter, over the course of a decade, over the course of a time that some particular person is their CEO. Right? They look at all these different things and they build their data and understand their product or their company or however they work based on all of those things. Pick different intervals and look at the average profits over those times. Does that make sense? Okay. Here we go. Nothing all that interesting or all that trickier here. Just it gave us the function. It doesn't actually give us data. It's giving us the function. So we have to find f at 2 and f at 5 first. So f at 2 is 2 squared minus 2 times 2 plus 5, which is 4 minus 4 plus 5, so that's 5. And the next one is 5 squared, which is 25, minus 10, which is 15, plus 5, which is 20. We don't really have to show work for this. We're going to cut to the chase and just state the values here. But you certainly can show the substitution step if you want. And you know that the order doesn't matter as long as you're consistent. So I'm going to start with the 5 on the bottom. But oh my gosh, like this really is grade 9 stuff. So don't mess this up. Don't put the X's on top. Don't put the run on top like it's rise over run. Make sure you're getting the right thing in the right order, right? This is really important, and this should be something we're good at. That is a mistake, certainly, that people make in grade 9 with this stuff. But by now, I hope that we're not going to. So if I start with the 5, I'm going to start with the 20 on top. And that's 15 over 3, which is 5. In this case, we don't have units, so it's just doing some math. It really is just calculating the slope between those 2 points. But again, that's a quadratic. So this is not exactly what we did in grade 9, but it's not really harder. Okay, f at 2. Oh, we already did that. It's 5. F at 2.5. What does that work out to? I got 6.25. So that's about it. Okay. Any questions about that? So there you go. If you want to write that down, the average rate of change of y equals f at x with respect to x over an interval. This is just a fancy way of saying rise over run. So, but over the interval from x1 to x2 is f at x2 minus f at x1 over x2 minus x1. So function notation is the same thing as y2 minus y1 over x2 minus x1. It's the same slope formula that we saw in grade 9. Questions? I think we'll talk about this a little bit more tomorrow, but there's a little blurb at the bottom there too that says graphically the average rate of change is the slope of the secant. Because again, now some of what we're talking about is curves. In grade 9, we were finding slopes of straight lines. We're finding the slope of a line. But now we're talking about, well, we may or may not be. Some of them might be straight lines, I don't know. But some of what we've done is 2 points on a curve finding the average rate of change between them, which is the line, the straight line that connects those 2 points on the curve. That's the average rate of change. Okay? And that's called the secant. A line that cuts a curve in 2 places is called a secant. It's the slope of the secant that passes through those 2 points. You don't write this down, but just watch. As I said, it's really important to think about what the average rate of change represents. So take a look at these two, and if you've taken physics or if you've done a lot of science, you've probably already done lots of this, and this is going to be easy for you as well, but maybe some of you haven't done it or find it tricky.
Will be work on the fire alarm at this time. If you hear the fire alarm go off, please ignore it. you know when the alarm has been put back online. Thank you.
So this is distance and this is time. So the distance is going through a consistent change over time, right? So what's the average rate of change represent in this case? If I found the change in distance over the change in time, distance over time is speed. That's what we already looked at previously, right? So the average rate of change in this case would be a measurement of speed. That one's very straightforward. You do a lot of that in grade 9. But what happens when the vertical axis itself is speed? Yeah, so some of you have done this. Cassie? It's acceleration. So the speed at 1 second is 2 meters per second. At 2 seconds, the speed is 4 meters per second. At 4 seconds, the speed looks like 8 meters per second. So the speed is changing over time. What does that mean? That's acceleration, right? And that's the relationship which, if you've done it in science, and some people it really clicks for, but for some people they struggle with this idea of what does the rate of change represent? Like, it's not always speed. So in this case, it would be acceleration. And if I were to plot, and this is where calculus comes in, which we don't quite get to yet, but if I were to plot distance of whatever this is, what would that look like? That's not something you need to actually worry about right now, but that's like where this thinking is headed, is that relationship. And the last one I just found a random graph. Global surface temperature. So for a 12-month running mean or 132-month running mean, I don't know exactly what those mean, but what would it, like, this is just a scatter plot that does that, it doesn't have a line of best fit. It's just got, like, literally the blue line is just connecting the dots, and then the red line is kind of like, I guess, the average change between some intervals in there, that sort of thing. But if I picked 2 points on the red line and found the average rate of change, you see that sometimes we call it the AROC, between those 2 points, what would that be representing? Right? So that's the kind of thing that as you're working on this today, if it's just distance and time then speed, that one's easy. But when it's something that's different, I think it can be important to really stop and think about, well, what is that actually measuring? Does anybody want to go ahead? Yeah, like the change, because the scale is annually, so in time. So the temperature, that says anomaly, it just means change in temperature. Oh, from 0, is it going up or going down? How is that changing over time? And you can see that eventually it increases a lot. That's a big problem on the planet right now, as you all know. But what would happen if I found, like, if some politician who didn't want to believe in climate change, like, they could pick points on this graph that would show not what's actually happening, not the trend. I could pick these 2 points, and the average temperature change between those 2 points has dropped. Or between 2 points that are really close here, or really close here, I could show that it looks like there's a little drop there just after 2000. So I can say, hey, look, things look fine because it was decreasing. But if I look at it over the course of a bigger period of time, you can see the real trend. And that's like getting into real world math, is how do you interpret the data, and rates of change and stuff definitely plays a part in that. Any questions? That's the last example. All right.